So today's lesson is going to be English, as I've been told. I hope it isn't too hard for you having 5 hours of lesson today. But I hope that it is going to be interesting, as this market is an emerging market for the last few years, and hopefully there will be many future professional opportunities in it. So it's really important to know how this technology works. And first of all, my name is Fernando Moreno. I work as product manager in a company named Cymec. We develop wireless sensor network products, and we create solutions based on that technology. First of all, I'd like to know a little bit which kind of professional profile you have, because I know that this is a very cross-functional master, and maybe some of you are quite related to the IT technologies, but some of you, maybe you are more focused in geographics or so. So it would be of some help to me to know which kind of expertise or experience you might have in the technology sector. So if you could start and please tell me your name, because obviously I'm going to forget it all along the session. I'll try to focus, but if you could tell me your name and why, which is your previous experience with technology, and which is your major area of expertise. First.
My name is Angel. I have not experience for this master is possible in GIS or remote sensing, but I had an FP course about trends, not too much about it. So,
okay. My name is Emma. I study surgery, and I don't have any kind of experience in it.
Okay.
I'm a career and geographer. We have experience in
My name is Juanjo. I don't have experience with wireless sensor network, and I am studying geomatics and engineering, tensor.
I'm Maximo. I have studied environmental sciences, and my partners I don't have any experience.
So I'll try not to be too technical for this session. There are some technical aspects that are important to understand the technology, but I'll try to be as understandable as possible in order to make you easy to understand this technology, and above all, to provide you several tools to be able to decide in the near future, when you are working in your professional careers, to know what this kind of technology can offer to you and which benefits you can take from them. So I would also like to know your experience as professors, because you're part of this class, of course. There's no distinction. So if you could give me a little piece of detail of your expertise, it would be a lot of help.
Yeah, I have experience along with
No experience with technology.
Me, I'm interested in the application of these things to the remote sensors.
To that, sorry?
Remote sensors.
Okay.
But in this case, the current is not, it's pretty much better.
Okay.
No, batalla un expert en remote sensing, but
Okay. Then this is going to be a introduction session to wireless sensor networks. Let's begin. Well, as Javier told before, I'm gonna give you 5 main modules. The first one will be an introduction to wireless sensor networks, in which I'm going to explain the history of this kind of technology and how it has been deployed and why it has been deployed, such technology for nowadays applications. After that, I will give you a little amount of details about technology and protocols. Then I didn't know your previous experience, so maybe it is quite technical, so I'll try to modify it in order to make you understand several things and to point you the main aspects of this kind of technology. After that, we'll talk about probably the most interesting part of this session, which is applications and related concepts, because this kind of technology, it's been used in many different contexts, and there are many concepts around this kind of solutions that maybe they are quite confused, but with this module, I hope you can get some lights into it. The fourth one will be an activity we're going to make among each other. We're going to define a wireless sensor network application of your choice and try to develop it and try to find which are the key points to define in order to look for a solution or try to deploy this kind of devices. And the fifth one is going to be focused on string learning management, which is part of the tomorrow's activity. You're going to be trained in the usage of this kind of technology, and because of that, I'm going to show you which benefits and why these kind of solutions are applied to wireless sensor networks nowadays. At first, I'd like to point out that sensor networks are not a new thing. They have been existing for a long time ago, but they've been mainly focused on production environments. Why? Because in the production industry, they have to take a lot of care about waste management and efficiencies in the production process. So wireless sensor networks, not wireless sensor networks, sensor networks provide them a tool to measure their performance and to enhance their activities in order to reduce costs and thus increase benefits. The beginning of this kind of technologies could be in the 1970s with the adoption of the PLC, which are called programmable logic controllers, which became important in factories as a way to automate factoring processes. Later, in 1978, the first sensor protocols like MAPUS were adopted, and they allowed factories to monitor and act remotely to their installations in order to create a good environment for production and very efficient in cost savings. Since then, a lot of technical solutions have been deployed, especially in the field of wired technologies, such as CAN bus, Traffic-Bus, EtherCAT. All these kind of technologies are well spread all along the production industry, and they have been used a lot for quite a lot of years. We're talking about 40 years or so. But why were factories the first who were interested in such solutions? Well, as I told you before, they had a really important need in getting information, in gathering information. Why? Because quality management relies on information. You cannot improve what you can't measure. So if you want to enhance your quality management process, you need to get some information from the process you're doing. For that reason, they were very interested in investing money and effort in developing such solutions. What did they use for that? They used sensor. A sensor is the basic unit that allows us to get information from a physical environment. A sensor makes the translation between a physical parameter such as velocity, temperature, humidity, or so into a measurable parameter from an electronic point of view. So this way we can gather this kind of information and then digitalize it and send it to a software tool in order to make a good usage of it. But why at first were sensor networks only used in factories. Well, as I told you before, factories were cost-driven. Their main purpose was to reduce costs in order to increase benefits, because that's what the business is about. And what happened is that these kind of technologies were really expensive, so they had to be well planned and well seen as a way you could have any kind of return on the investment you were making. At the same time, they were really complex infrastructures. They were wired technology. They used wires for communication, and that implied a lot of effort in terms of deployment. Imagine that you want to deploy different sensors all around your home, and you would need to get a wire through every part of your home just to get a daily information from your living room or your kitchen, for example. That it is really difficult to do because that implies a lot of deployment costs. At the same time, the fact that this technology was wired, it had limited scalability. What's scalability? That means that these kind of systems can grow. When talking about information, we usually tend to think that the more information we get, the better we can improve several aspects of our business, of our daily activity, or everything. These kind of systems have a limited scalability. They couldn't grow as in the way that wireless technology can, just because of the fact that you have to make civil works into the streets or into your factories, and that way you couldn't make such big deployments as wireless technology could allow. They also had an important disadvantage. It was that as they were developed by companies whose aim was to be profitable, and the purpose on that was that they were the only ones who had such technology, because that was an advantage in contrast to their competitors. These systems were not too interoperable. What does it mean? It means that once you get this kind of product, you're attached in some way to this technology. So you can't buy any other product and make it work within your organization without incurring in many operational efforts. I mean, today we are very used to mobile devices, and as you know, for example, there's a very popular protocol called Bluetooth to share files between devices. Well, that allows that we all have different devices from different vendors, and we can exchange files easily because of the standard. Okay, that's because this is a mass product, and the aim of this kind of technology was to interoperate to each other. But at first, sensor networks were not like that, because this kind of technology implied a really advantage to other competitors, and that this is the world of markets. They wanted to be the best ones and the lowest costly in the industry. So because of that, and because of the technology deployment, this was not solved before, just because there was no interest. No, it is just because it is a difficult task. Wireless sensor networks have different challenges. The first one would be low power consumption. If you have noticed, I've been talking about sensor networks' main disadvantage, the fact that they were wired. Wires are an advantage in a way that they provide reliable communications, but on the other hand, they are difficult to deploy. As I told you, you need to do several works within your environment or your infrastructure. For that, the wireless sensor networks pretend to eliminate all kind of wires, both for communications and for powering. So if you want to erase all wires for powering, you need devices that have low power consumption. That means that they can be operated by batteries for long life times. So they need to consume very little energy. If you can't provide this kind of device, then you will have to set a wire at least for powering, and then if you have to make your works to provide a wire for power, then probably you will be able to get another wire for communications. You can share costs. On the other hand, they must be low-cost devices. In contrast to classical sensor networks, this kind of technology must be low-cost. Why? Because what this kind of technology wants to propose is to get a higher dimension in the way we get information from the physical environment. We want to install a lot of devices, a lot of sensors that take information from the environment. So they need to be low cost, because if you want to deploy a lot of them, the overall cost is going to be huge if their individual cost is high. So the more you can reduce its cost, the little the budget you will need to deploy a solution. So this is a trade-off between technology and cost as well. And as I told you before, both challenges are also applicable for sensor technologies and communication systems. Not only, I'm talking about especially low power and cost. There is a part that is the one that provides communications, but the other one is the sensor, as I told you, the one that is responsible for taking the information from the physical environment. So you need to get those challenges to sensor technologies, and the sensor industry hasn't been so deployed until a few years ago in terms of low cost and low power consumption, especially with the adoption with new sensor technologies which are really small, and we have them in our smartphones nowadays. That's the reason why our smartphones might have between 15 and 20 sensors on them. And then the beginning of this kind of solutions. As almost everything in the technology industry, it came from the military applications, especially the US Army. Imagine a solution that needs no wires to communicate and to offer information. That had an important advantage in terms of military operations. They could spread sensing nodes from aircrafts and get information from the battlefield prior to the Army arrival. So prior to arriving, they could get a lot of information, not only environmental information such as temperature, wind, or so that could affect parachutes, for example, to land on Earth, but also information about presence, and they could identify which areas were without any people, and they could get into the enemy's land through this path. So their aim was to provide nodes, which they called modes, and it is a really popular word in this kind of technology. They created those modes to create autonomously a network without doing anything, without any human interaction. They could throw them into the battlefield, and they would create automatically the network and get the information remotely. So that was really important. Because of that, there was an international interest in deploying a standard for this kind of technologies, because obviously there are not only applications in the military service, also in the consumer's industry or in the factory or production services. Because of that, in 2003, so we're talking about a really new technology, the IEEE published the first standard for low-power wireless sensor networks. It's called that way. IEEE 102.15.4. It is the same group that created the Bluetooth technology, and its aim was that to create a low power consumption technology to allow the development of this kind of solutions, wireless sensor network solution. And they created this standard in order to match the both challenges that I told you before. First, the low cost challenge, and secondly, the low power consumption challenge. And because of this standard, many other standards have been created on top of that. Later, I will show you a little description of how standards work, so you can understand this. But many different technologies that are the famous one, the one that which are printed in consumer products, such as Zigbee, Secure PAN, Wireless HART, Z-Wave, and so on. Many of these technologies could have been created because of this basic standard, which is public, free, and open. Okay, so now I end up with introduction. Please, if you have any question of if at some point you feel I'm going too fast or you need more detail of a certain thing, please just tell me, because I come from the technical business, so maybe for this I don't know which is your limit of what is understandable or not. So please feel free. By now, is it okay? Did you get more or less the whole message? Now it's going to be the more technical part. I will try to make it as affordable as possible. Okay. Now, as I told you, I'm going to talk about technologies and the basic features that make these technologies so interesting to deploy, so we can understand later the kind of applications we can develop with such solutions and why we can apply them, and obviously to distinguish whether we can apply them or not, because obviously everyone is going to tell you that this kind of technology is the best, but there are several applications where it is good to use it, but other ones which are not needed because there are other solutions that might be applied with the same or better performance. So I want to give you a little sum up about this technology basics, and then you can understand later the applications and even think by yourselves about different ways of using this kind of solutions. First one, I'm going to give you the key of low power, which is, people don't usually talk about this, but it is really important to understand why we can have devices battery powered for long life, for a long time. We're talking about devices that can be powered on batteries, on AA batteries, which are the batteries that are used in this remote controller. 2 batteries can last for 2 years or more. That's a really long time talking about information systems. And there's only one basic rule that allows you to get the low power, which is called the Daddy cycle. Daddy cycle is the percentage of time you're doing something in contrast to the rest of time. So the key of this kind of process is that they are going to do one thing in into different times, but the rest of the time they're going to remain in a really low power state. They are going to hibernate, like the bears in winter. They're going to remain in a really low power time. So this time they are not doing anything but waiting for the next time they need to give the information. So,
No, es verdad, como que hay
so between this time and this time, these nodes are doing anything. They are only counting when time do they have to wake up, and then they will wake up, do what they need to do, and then sleep again. So this is as easy as you see, which is the key of this technology. Well, they need to be asleep for a long time, the time you want, and this power consumption isn't zero. It must be as low as possible, and that's the key of this kind of technology. But there's also another point that when they need to wake up, they will wake up really quickly. I mean, it is not like, for example, me in the morning that I take half an hour to wake up. They need to wake up really, really fast. So they do it in less than a millisecond, and thus they can do what they need to do and then sleep again without consuming much energy. So imagine that these devices are doing a very small activity at certain times and then sleeping again. Here we have different times, that different concepts that you will often find in product data sheets and so on, and which is, for example, the sleep time, which is the time that these kind of nodes remain slept, the active time, which is the time they take to get information and then send it to the software that is managing the installation. Then it is a sampling time. This is the time that the device is going to transmit its information. So, for example, if we're talking about a sampling time of 1 second, that means that a device is going to give us a measure each second, 1 second after second after second. The more we set this time, the more energy we are saving, because this is the time. Oh, again. Because this sleeping time is going to be bigger. So active time is the lowest as possible, and the sleeping time depends on sampling time. If you want to get a temperature every 30 seconds, and you have an active time of 100 milliseconds, then you make the rest, and then you get the sleeping time, which is the key of low power. And then you have three different levels. That you have zero consumption, which would be the ideal state when a node is slept, but it's not possible. We don't live in an ideal world. And then we have the sleep mode consumption, which is the minimum energy consumption that our node is going to have, and then the active mode consumption, which is usually the highest one we're going to have during this time. Okay. So the key is, well, you need information. Set how much information do you want, and how often do you want it. And the more you can set this sampling time, the more energy you're going to save. So, for example, we often tend to think that in a system, the more information we get, it is better. But we must make a trade-off between information and this kind of solutions. For example, you might say, well, let's be overrated and get one measure every second, but I don't need this kind of information. That way you are wasting energy with no purpose. Imagine a process that varies only once a day. For example, you want to detect the sunrise or the sundown. Those are really slow processes. So there is no need in having a 1 second sampling time. Why? Because you don't want to measure the sunrise or the sundown each second. Maybe it is enough with 1 minute, and then you're saving more energy, and you will deploy a solution that will last, will take the most of its batteries for a long time. So this is a trade-off between what you need or what you want or what you get sometimes. This is an example. I will not make a lot of effort in this, but you might have an example about the difference. Just focus into these lines. Here you have the whole process, but look at the difference between a sampling time of 1 second or 15 seconds. The same device would last with the same batteries 45 days when at 1 second sampling time, and 662 days with a 15-second sample time. So you might see this huge difference. It is almost not exactly proportional to the difference between sampling times. Not exactly, but it is quite close. So what does it mean that when thinking about these kind of solutions, you have to be really aware of this fact. Not because of having a lot of information, we are deploying a better system. We need to get the information we need to, because think it another way. This information can be huge when talking about these long-time systems. If you are monitoring the environment for a year and you're getting a sample each 1 second, just imagine how many samples are you going to have each 1 year, 2 years, 3 years, a lot of time. And then you will have to storage it, and then you will have to treat it, which is really important, to translate this information into knowledge, into what does it mean, this information, because a temperature might mean different things depending on the environment it has been deployed. So you have to be really aware about this fact. You need to think about the overall system and see which kind of battery life I want to have, and how many information I like to know. Okay. Here you will find the 3 main parts of a wireless sensor network node. The 3 main blocks that compose it. First of all, the sensor. As I told you before, this is the key of this kind of systems. You want to get information, and sensors are the only way to get this information without human interaction. So we need sensors that get information from the environment and translate it into something which is measurable from an electronic point of view. So sensors are a key point into these technologies. Later on, I will make a specific explanation of each of these ones, so you will get the basics from this one and how to use them and so on. Communications. Obviously, once we get information, we need to communicate it, to transmit it to center software or center databases or so, in order to create knowledge and create several actions into the field you're working on. So this module is responsible for creating a communications network and then make sure that the information gets to its destiny, and then the process is done. And the third one, which is really important, power management. How are we going to manage the the batteries or the power source we're using for this kind of devices, because an appropriate power management is key in this kind of systems. Later on, I will talk to you about this kind of things. Now, sensor technologies. Now you got the three main models, right? Well, talking about sensors, imagine that you want to create a solution. This is not only a technical thing, because just imagine most of you are geographers or environmental science. Imagine at some point you will have a need, or you will need a certain measure. So you need to know which kind of technology you can choose, and then make the proper solution. Imagine that, for example, for environmental scientists, you want to measure CO levels or CO2 levels for cities or so, then you will have sensors for that. But on the other hand, geographers, for example, I don't know, maybe you want to know height from the sea level, or I don't know, sorry, but maybe other kind of parameters. And what you're going to look for is a sensor technology. You're going to look for if you want to measure a temperature, then you will go through a thermometer. So then you need to know this kind of classification. You will have mainly two kind of sensors: analog sensors and digital sensors. Analog sensors are the ones who offer an output which is in some way correlated to the physical parameter they're measuring. We're talking about a sensor which translates the physical parameter into electronic measure, such as resistance, capacitance, inductance, or a voltage current output. This is all electrical parameters that can be measured by electronic devices. So what is important about this analog sensor is that you will probably have a sensor that makes you a formula, which is the relationship between the physical parameter that you want to measure and the electrical measure you're going to get. And then imagine that you have X value of resistance. That means that value into temperature, humidity, or a flow level, or whatever you want. And that's the key point. On the other hand, we have digital sensors, which are a more sophisticated technology, which provides this kind of reading, but in a digital way. So you're reading ones and zeros, like in digital technology, using which is called a digital bus. The digital bus is a group of wires that allows you to read something. A digital bus would be the Ethernet we use for our computers, or the prior Modbus, the Modbus technology I told you in the production environment, and so on. And which is important about sensor technologies is that from 10 years to now have been appearing new technologies that allow new ways of measuring, especially which is called MEMS technology, micro electromechanical systems. This is a MEMS sensor. Those sensors are really tiny sensors that allow you to measure different physical parameters as all sensors, but in a really reduced way and really reduced cost, because they use specific materials that there are no electronic circuits inside of them. It is just the material which gives you the physical parameter instead of a circuit, an electronic circuit or so. So that way they are produced in huge quantities, and they are really low cost, and at the same time they have a really good performance in terms of resolution, accuracy, terms that I'm going to show you, I guess, right now. No, right, yes. So you have mainly those kind of sensor technologies, analog sensors and digital sensors. But when it comes to a whole wireless sensor network system, there are three important concepts that are really important, especially when talking about low power consumption, which, as I told you before, is the key of this kind of technology. The first one is the warm-up time. Once you want to use a sensor, you need to switch it on. You need to give it certain energy in order to make this kind of translation between the physical world and the electronic world. There is a gap time you need to wait before this kind of measure is valid, it is good. This is called the warm-up time. As I told you before in the timing diagram, that once you decide to wake up, you need to wake up as fast as possible. The warm-up time in the sensor is probably the most important specification when talking about this time, because communication technology, it is well solutioned, but when talking about sensors, there are so many types of sensors and technologies that each of them have a warm-up time. So imagine that you want to get a solution which must be really low power, and you have different options, and then you might take a look at the warm-up time, and probably imagine that there is a sensor that has a warm-up time of 1 second, and you want to have a measure every 1 second. It is impossible. Why? Because you need to wait 1 second to get the measure. So you can't get one measure each second unless you keep the sensor always powered. So this kind of information will allow you to decide if the solution that has been presented to you, or you can choose via searching on the internet, it is suitable for your application, or is it possible for the kind of solution you're looking for. The second one would be current consumption, which is the way we measure the power consumption of our system. The current consumption, it is like the food we give to sensors in order to provide the measure we need. So the more is the current consumption, the more needs we will have of power in our device, and then we will consume more energy, and our batteries will last little. The third one would be operational voltage. This means that a sensor consumes a certain current related to a certain voltage. Voltage, for example, is the level you will have in our electric plugs, which is in Europe 230 volts. That's the voltage. The higher the voltage is, the higher the power we need to feed this kind of sensors. So then, if you want to get a good overall solution, both of these have to be low, because power is measured as voltage times current. So they are both related to power consumption. So maybe you will get a sensor which has a really low current consumption, but at the same time it will have a high operational voltage. So as the power, it is voltage times current, then the overall power, it is high. So you need to make this kind of comparison between those aspects. They are related to each other, and they cannot be separated when analyzing this kind of technologies. And here there is these three concepts are also the key to distinguish sensors from a commercial portfolio or commercial brochure. Why? Because here it is where manufacturers try to make this kind of marketing concepts. They are really, really different, and I will show you why. Accuracy. Accuracy is the way that when a sensor gives you a measure, if this would be the measure, how close it is the measure from the actual measure. So here, for example, this is a really accurate sensor, because it is in the center of the spot. At the same time, we also have another parameter, which is called resolution. And that's the one that usually manufacturers give. Why? Because resolution has nothing to do with accuracy. And we need accuracy for sensors. Resolution, it could be defined as how far you get into decimal numbers when given a measure. For example, if I'm talking about measuring temperature, and I tell you that this room is at 19.543 Celsius grades, then my resolution would be 1 part over 1,000 from the overall measure. But probably my accuracy won't be that way. It can be, for example, 1/10 of Celsius, and because of that, manufacturers usually tend to give resolution. But what we want to know is accuracy, because accuracy is the term that relates the measure to the real measure what we want to get. So when reading a data sheet from products, we have to take a lot of care into getting this kind of information rather than this, because this is only a math thing. I can give you as many decimals as I want to, but what we need is accuracy. Finally, we have repeatability, which is another kind of parameter, and it gives you the way that if you make several measures, how far are they going to be from each other? And for example, this kind of sensor will have low accuracy and low repeatability. Because if you see, you get different measures, but they are really far away from each other. At the same time, both two measures have the first one will have high accuracy, but the other one will have low accuracy but high repeatability, which means that once you make a measure, you will get all measures close to them, and that allows you to create a way to compensate this kind of error, because you will probably get if you do it once for one measure, then you can set a rule to compensate it in a near future. So this is not a big problem. This is a huge problem, and you could cope with this kind of situation. This would be the ideal situation, but obviously this situation is going to be really expensive. But this kind of situation is not copable, because it is really difficult to set where the errors are. Maybe you could set a mean among all the measures, but depending on the source of the error, you won't get an appropriate measure. This kind of sensor is affordable because they are usually cheap, and at the same time they can be compensated in a future. Well, and which is also really interesting about wireless sensor networks is that although they are named sensor networks, they also imply actuators. So what does it mean? It means that I get information, but I also have the ability to make an action into the environment I have my deployment. So imagine that we're talking about this room. We have presence sensors that detect whether there is a person or not in the room. And once there is no one in this room, the actuators will switch off the lights. That's a typical solution. That way, although we're talking about wireless sensor networks, we're talking about wireless sensor actuating networks or so, because they have bidirectional communication. That means you can get information, but you can make actions to the physical environment. And that's really important because they allow you to create enhancing policies. They allow you to get information, analyze it, and then act autonomously via this kind of solutions. This is the example I told you. And typical actuators, for example, are relays, which are just like the switch, the light switch here, that switch on off the light. Dimmers, who are the ones responsible to dim the light, to set different light levels within a room or in the streets, or analog outputs, which are just actuators that give you this kind of output and then set a different behavior depending on the device you connect to. Now, power management. We are always going around the concept of low power. We're talking about almost every time about battery powered devices, and here this is just a little spot. We have a plenty amount of different battery technologies, like on the nickel cadmiums and so on. We have a lot of them because we are living in a battery-powered world in many different fields. Each of them will have their benefits or disadvantages. This would be a whole 5 hours session if we wanted to. And which is really important is that, well, we need to use batteries, but we need to ensure that we are using them with low-power devices, because if we are not doing so, we're not going to get any kind of advantage, so it will be no sense. And which is important is that sometimes, as I told you before, some sensors are not suitable for battery powering. For example, optical sensors are really difficult to be battery powered, especially laser sensors, because they need a lot of power to operate. So it is difficult to battery power this kind of solutions. And at the same time, sensors which have long warm-up times, as I told you before, if they take a lot of time in warming up and getting a proper value, it is difficult to set a wireless sensor network solution with that technology. But what happens is that usually there is a need of using this kind of sensors within a whole wireless sensor network solution. And what happens is that you might have battery powered devices and at the same time power line powered devices. It is not compulsory to battery power all the devices. You can choose, but then you can make them coexist into the same system and take advantage of different solutions into an integrated environment. And here, this is a concept that it is quite interesting nowadays, which is called energy harvesting, and it stands for the way we get energy from the local area we are in. The most popular one would be photovoltaic panels for solar energy, but there are other kind of technologies whose aim is that these nodes can be operated for a long time with batteries for 2 years or 3 years, but just imagine that we can get a little amount of energy in the place they are deployed, and then we can get their battery life to 5 years, 10 years. It is told that maybe they can be completely autonomous. So there are other technologies rather than photovoltaic panels, such as temperature energy harvesting or vibration. The vibration, it is vibration energy harvesting is a technology that allows you to create energy from movement, from vibration. And it is really suitable for when talking about structural monitoring. Imagine you want to get information from a truck or cranes when talking about civil construction or so. They are always vibrating, and you can take advantage of this vibration to enlarge battery lives. So these kind of technologies are really new. They have been deployed for the last 5-6 years and provide really interesting applications in the near future, because we will have the ability to create energy locally, which is the tendency right now almost in every aspect of life. Well, now I'm going to make you an introduction to the basic fundamentals of this kind of technologies, and I will point out several important aspects of technology and why we're getting the main challenges we were talking about: low power and low cost. But first of all, I guess that you won't probably know what is this. This is which is called a protocol stack. Okay, this is a way that we develop protocols and technologies. We set different levels, and each level has specific tasks in order to create a complex system. So we divide the work into different layers. They are called layers, and each one relies on the previous one. So this layer serves the next one and the next one with many functionalities, and then we can locate problems or areas to enhance or so. Usually, I will try to be as brief as possible. Physical layer, for example, stands for what is related to the physical world. In communications, the physical layer will say if you will use a wire, which kind of wire. You can talk about copper wires or fiber optics. If you're talking about a wireless technology, this kind of parameters that are basic. Then data link layer talks about how nodes communicate to each other. For example, if my computer is attached to a router, the data link layer will get the foundations in which my computer will talk to the router. Okay, and then the network layer will create the functionalities in a way that my computer can talk to a computer in the lab, for example, within the same network, but which are not directly connected. And that way we go into applications which are finally programs into our laptop computers. That's in a very simple way, but just I wanted to get that physical layer remains to the things we can talk about, which are related to the physical world. Data link about how a device which is directly connected to other devices communicate, and network is how devices communicate within a whole network. The laptop example is really good, because network will stand for the communication between my laptop and other laptop in the lab, data link laptop router, and physical the Ethernet wire. Don't be shocked by this scheme. This is the protocol stack for Zigbee 802.15.4 protocol. This is the whole image of how wireless sensor networks technologies are built. Okay, here you have the two basic layers, as I told you before: physical, which stands for physical world, medium access control, MEC layer, which is the data link, a part of a data link layer. So it stands for direct communication, and then the rest of them, network and application. You won't need every layer for all technologies. Just keep that image, because I'm going to tell you the clues in each of one, each technical clue without getting too deeper into them. So now just keep this image on map, and I will try to explain to you. Okay, when talking about wireless sensor networks, physical layer, that means, as I told you before, the way that it communicates into the physical world. We're talking about a wireless technology. As the acronym stands for, we're talking about a wireless technology, and it uses 3 different frequency bands, which are called frequency bands, which are the same as our TV channels. It is the same term, and our 3 bands are centered into 3 open frequency bands, which are the 2.4 gigahertz with 16 channels, the 868 megahertz for the European Union with a single channel, and then the 915 for the US. These bands are free to use. They are called ISM bands because they are for investigation and science and medical application or something like that. And which is important, for example, this band is used for by other technologies such as Wi-Fi or Bluetooth. It is free to use, in contrast, for example, to TV bands. As you know, TV channels have to pay for these bands. These bands are for free and are suitable for low power devices and this kind of things. And which is really important also is that we have a total bandwidth of 250 kilobits per second. This is a really low bandwidth compared, for example, to Wi-Fi. We are used to talk about internet connections of megabytes or so. This technology has really low bandwidth. Why? Because the more bandwidth you have, the more power consumption you will need. Imagine when you're running. If you run fast, you need more energy to run fast, and if you are walking slow, then you will need lower energy. So this is important because we are talking about wireless sensor networks not as a wideband solution, as Wi-Fi, for example, to communicate to internet. We're talking about low bandwidth solutions. That means we only want small information and not too often in time. We're talking about that in wireless sensor networks, we never get an application under 1 second sampling period because you won't have the ability of having a low power device, and there is no need here. What we're talking about is of measuring processes which are not really fast. We need to have one sample each several seconds, several minutes, several times a day. So we're talking that we don't need a high bandwidth for such solutions. So that's the key. Sometimes people ask, well, can I integrate a video solution, video streaming solution into a wireless sensor network technology? Well, you won't probably because you don't have enough bandwidth, and this bandwidth has to be shared between all the devices into your deployment. So it is for its purpose, which is getting information, not too often, but in terms of seconds, minutes, or hours, and then having a lot of devices getting that information. So you don't need much more bandwidth. Actually, this bandwidth is overrated, and we don't need so much. here there are two concepts. A digital modulation is the way or the shape we give to an electrical signal. For example, if you have ever taken a look into the electrical signal from the electrical plug, you will see that it is a sinus, more or less, and that's the shape it has. Digital modulation gets different shapes, not a sinus, different shapes. And wireless sensor networks uses this digital modulation. That means that it provides a constant envelope signal. It means that the signal always have the same voltage in the output. That is really important because it means that we can produce really low-cost technology and really efficient technology in terms of power conversion. When we want to amplify a signal, if it is a constant envelope signal, it is easier to be amplified, and thus it is cheaper and more energy efficient. And on the other hand, you also use another technique, which is called spread spectrum techniques by direct sequence, which means that instead of using a narrow band into the frequency domain, if you want, you have a signal into this place, you will spread it into a more space, and this way they are more robust against interferences. Why? Because we're talking that we are using a free band, and there are a lot of technologies operating into this band. And we want to avoid this kind of interference, because otherwise we won't get reliable communications into these systems. And what we want to have is constant information along our systems life. The link layer. Link layer, as I told you before, is the responsible for communication between devices which are directly connected. The example of the laptop and the router. So it has some features such as node association. It means that allows a node to join another node. It gives addresses such as in the laptop. And I don't know if you know that we have the IP address, which stands for network, and then the MAC address, which is a unique address, which is in the hardware of our computers. So this kind of addressing would rely on the link layer, and then has different features related to security and robustness. A frame control check to know if there has been any mistake in the transmission of the frame, and then an encryption to avoid anyone to take a look at our data without any permission, because we're talking about wireless technologies. Imagine that we could do the same as happened in Deusto a few moments ago. Then we need to encrypt communications in a very secure way, because wireless sensor networks often deal with really sensitive information, especially related to industries and buildings. Here, the link layer defines two kinds of different roles of devices. The first one would be a first functional device, that stands for first functional device. It is a device that has all the capacities of forming networks and doing all the things that they need to do. And the other one would be the reduced function devices, which are devices that are really dumb, really silly. They just only take the information and send them, and without any other capability within their network. This is done because the simpler the device is, the lower the lower power it will consume, and the lower hardware requisites we will have, and thus they will be cheaper. When we make something simpler, it is always cheaper. here it is the way that nodes can communicate to each other. We have three main different network topologies. This form of networks are called topologies. The first one and the simplest one will be a star network topology, in which there will be one central node, and then the other ones will communicate directly to only one node. This is really simple. This is like the boss of all of the rest of the nodes, and this would be connected, for example, to a PC or a database. The second one in complexity order would be the cluster tree, which is an extension from the star network. It is a central node, and then a second level of nodes, and then stars progressively into the network. It is like a star topology, but different levels. If you have this will be only one level, and here you will have, for example, two levels. But we can extend it as much as we want. Okay, and the last one, and which is really interesting for wireless sensor networks, it is the mesh network. What does it mean? It means that when I told you before in the introduction about military operations that they wanted to throw modes into the battlefield and get them a network formed automatically, this kind of networks were the purpose. Why? Because these networks, what they do is that every node communicates with every node within their coverage area. Okay, every node communicates to this node, to this, and to this. And then, if this link fails, it has an opportunity to transmit its data through a different path. But for example, in this way, if this node fails, these two nodes would remain isolated, and you would have no chance to communicate its information. And in this kind of topology, it is different. But this is not for free, obviously. As I've been told you all throughout this session, the more complexity we have, the more requisites with specifications we will have for our solutions. So what happens is that although a star topology it is really simple, it is also really efficient in terms of power consumption, because these nodes can be really silly nodes. They need no knowledge about the network. They only need to communicate to this node and then forget about everything. And at the same time, here, these nodes must get some kind of information on who are their neighbors and who can they communicate to. And because of that, if you see, I told you before that there were two kinds of devices, full function device and reduced function device. And these kind of nodes, which are really smart, really intelligent, can't be reduced function device because they are really clever in terms of network formation. And the only ones that can be reduced function device are the ones located in the lowest levels of the network and as extension of a star network. They can't form a mesh network. And why is this really important? Because I've been telling you that wireless sensor networks technology rely on battery-powered devices and low-power devices and so on. But the truth is that the only devices that can be battery-powered are this one here. This one needs power lines to operate. This is something that usually people miss, they don't explain. We always say that, well, wireless sensor networks are really low power devices and so on, but the truth is that we rely on power devices to create this kind of networks. And what it is really interesting is that these networks can be formed by thousands of devices. So we're talking about really huge networks, but they rely on devices which are placed near to a power line wire. These are the only ones who can be battery powered. And don't lose that focus, because everyone's going to tell you that these ones can be battery powered, but they can't. The only ones can do is this one. This can be battery powered, but only for weeks, not for years like these ones. So it is a trade-off depending on the solution you want to deploy. However, this kind of solutions, for example, a cluster tree, maybe this kind of nodes can be battery powered because they have much less to do than these ones, because they have fixed rules to communicate. He knows he needs to communicate with this one, and this one with this another one, but this one will never communicate to this one. So there is a fixed rule that they don't need to think, they don't need to be clever, they know exactly what to do. I take your information from here and give it to there. So no problem. But here, the intelligence behind that, it is much higher, and it implies more requirements in terms of design. Talking about Zigbee, this is the way that Zigbee, which is the only standard for wireless sensor networks, completed the whole stack, as I showed you before. It is the only open one and the only standardized. It defines 3 types of devices. The first one will be the end device. The end device is the silent one, and which is in the last part of the network. These devices have sensors, give information, and are battery powered. Then you will have routers, which might also have sensors. You don't need to have a router just like that without doing anything but creating the network. These routers have the ability to get information also, but they need to be powered through power lines, through conventional power lines. And then, last but not least, the coordinator. The coordinator is a very special device within the network, which is the big boss of everything. And often, it also provides a way to communicate to other systems. And this coordinator, for example, at the same time it has wireless sensor networks communications, it will have all other kind of communication, for example, Wi-Fi, Ethernet, or so on. And that way, the information gathered from this node can be delivered to a central system in a different way through internet. For example, imagine that this node is connected to an Ethernet plug and has internet connection, and then every single information within this network can be accessed remotely through internet. Then, about the network and application layers in Zigbee, I want to extend too much. Network layer stands for, or within the network, as I told you, computer to communicating a computer to a computer in the lab, and that's the same way. It communicates nodes which are not directly communicated, and it has different other keys, such as another encryption to give more safety into the network, another kind of addressing, but this is an extension of the previous layer. And the application layer, what provides is the final shape of the device. It means that is the layer that gives the real features of the product. We're talking about an application layer that gives functionalities to a specific product more than the communications. And that's through what is called clusters. This is really easy. That means only that they are like bricks we use in the application to access to certain features of our devices. For example, there is a cluster called the on-off cluster, and that means that this cluster is a standard cluster used to switch on or switch off as a device. It doesn't mean if it's a light controller, an HVAC controller, or a laptop, or a wind turbine, or whatever you want. And there's also a basic cluster, for example, that provides basic information about the device. You can ask the device, who are you and what do you have? Then it will answer with a basic cluster. You're going to work tomorrow a lot with this kind of technologies. You're going to work with clusters, and you will see how easy it is to work with them, because they provide you really simple simple frameworks to know different information about the network, and it is just to ask and get a response, and even you can do a write activity, and then that would imply a certain action. For example, if you want to switch on the light, you will make a write into this cluster, and then a light will switch on, and that's all. That means they use what is called attributes, which are the properties of these clusters, and tomorrow you will see what does it mean, but this is just basic functional modules within a device. That allows different devices from different vendors to communicate each other without needing any kind of translation or adaptation or something like that, because they are really to speak the same language. If there is a device who uses this cluster, then other device is prepared to make usage of this one, and they will communicate each other without any problem. Other interesting thing, and this has very little to do with technology. This is more related to market and applications. The Zigbee Alliance, which is the organizations which take care of this standard, defines different applications profiles for Zigbee devices, and that is not a technical strategy, but also a marketing strategy. Why? Because they want to define different environments in which to use such technology, and they talk, for example, about the health profile, which defines different kind of devices which are standardized in order to make manufacturers to create products that will interoperate in a health environment for hospitals, clinics, or home assistants, or so on. And for example, other ones, building automation for automating building lights, different appliances, everything you might think into building, and integrated to security, home as an extension of the building, control in order to provide a standardized technology in which remote controllers could communicate to almost every TV without needing any specific code, and so on. Energy, which is really used in the energy industry, or light, which is a simplified way of energy to control lights. And often what they do for these profiles is they define devices they need for this. For example, if you're talking about light, they will define how you have to do a light controller. But if you're talking about health, they will talk you about how to do an ACG detector, and see how you can get all this information into a centralized software, and how to get usage of our windows or our Roombas or so on. For example, in the energy profiles, there are different devices such as smart meters, which take automatic readings from our energy consumption, load control, which are devices who make usage of of different appliances into our home, for example, the fridge or the oven, in-home display, which is a beautiful LCD display, which will show you your current electrical consumption and so on, and it defines different security policies specific to that, and which is really important. They define regulatory testing specifications. They ensure that all the devices that want to operate within a profile, they have passed a certain test in order to ensure that they can interoperate to each other, because the key of all of this is that, for example, for your home, you will be interested in creating an advanced domotic system, and you will get different devices from different vendors, the one for the lights, the one for your windows, the one for your kitchen, and they will have to interoperate each other. And that's a great advantage in terms of price and flexibility in the market and competition, which is always healthy when talking about technologies. The Zigbee Alliance, it is the one, as I told you, who takes care of this kind of technology. It is a non-profit organization, but it has been created by private companies, the most powerful technology companies in the industry, because they know they need to be standardized in some way in order to sell these products at this huge quantity of devices we're talking about. And it was created to create wireless sensor network standards over the first standard, which was public and open. And this one was created also with the same aim. And what they do is to create different profiles, as I told you before, and at the same time to ensure an ecosystem of products that can communicate to each other. So imagine you want to create a solution. If you go to the Zigbee Alliance, there is a huge portfolio of devices from different vendors, and you will say, well, I want to use this product from this manufacturer and this other one from another. Today, I don't want to work with Philips, I want to work with Schneider Electric, and I will switch them all, and I will have no problem in integrating the same solution. Of course, there are other wireless sensor network technologies, but they are not open or they are not standardized. The first one is Z-Wave, which is a wireless sensor network standard which was specifically created for home automation. This technology has been very successful in domotics, especially in the US market, because they provide really cool solutions. If you take a look at these kind of products, they look really good. It's like the Apple of the domotics, because they are really well ended and they are really beautiful. On the other hand, we have wireless HART, which is another wireless sensor network protocol, but this is an evolution of the HART protocol, which was one of the classic protocols I told you before in the production industry. They have made the movement to a wireless solution in order to continue to get customers in the industrial market. So this is not open, but it has a lot of advantages, especially when talking about manufacturing industry. And lastly, and with this, after that, we will have a break. The main trend when talking about wireless sensor networks, it is the IPv6 coexistence. Nowadays, wireless sensor networks nodes have their own technology, and they don't have proper IPv6 communications, which is the current standard for the internet, and which is the one which is the future for the internet. Now, what we have is when we take a look at the network from a Zigbee network, the coordinator would have IPv6 communications, but the rest of the nodes will not be accessible from any computer or so on directly. What is now being developed, what we're now developing in the industry is wireless sensor network nodes that are IPv6 addressable. That means that you can access these nodes in the same way you will access any other device within the internet. And they will have different services and so on. But there were two problems to adopt this solution into wireless sensor network products. The first one is that we have limited resources in embedded devices. IPv6 technology, it is really well. It has a lot of intelligence behind that, and it is difficult to get it into an embedded device, which is usually very restricted in resources that they might have. They have very little memory, and for that reason, some guys created from the IFTF, which is the Internet Engineering Task Force. These are the guys who create the standards for the internet. They created this protocol, which is called 6LoWPAN, which is a reduced way of the TCP/IP protocol stack for IPv6 into a more light solution. That way, they can be implemented in cheap technology and low power technology. And at the same time, they had to deal with a very important problem, is that if I told you that the key of low power was the data cycles, that means that the nodes are not available for a long time, for a long percentage of time. And that way, if you take a look when you're using the internet, internet relies on that every device within the network is connected and always accessible. So here they had to deal with different routing problems related to this fact that the nodes were slept and they didn't know anything until they had the next time transmission. So they got this kind of specification for this routing, which is special for wireless sensor network, which is called ROLL specification, routing over low power and lossy networks. And that way they solve the problem. This way, this standard is now introduced into one Zigbee profile, which is the Smart Energy 2.0. And that way we could extend all the software applications that we're using into our laptops to wireless sensor networks. And we can ask to any wireless sensor network node in the same way we do when we type a URL into our internet browser or so, and that gives a great opportunity for this kind of solutions to integrate not only with other wireless sensor network technologies, but also with other technologies such as Wi-Fi or Bluetooth, WiMAX, and so on. And this gives a wonderful site in a near future in order to use it in a really easy way. Any questions?
I have a question about the distance range of this technology. Because you keep on talking again, for example, with Bluetooth, with wireless installed in close premises.
Yes.
The distance is very short. So how large is one of these networks? Can I have one of them, for example, Espero Studios?
No. Here, what happens is that as we are working in a free band, there are regulatory specifications that block you to use more transmission power than the one that is allowed. And that's the reason why Wi-Fi technologies or Bluetooth technologies are medium range technologies. They can only transmit to 100 meters or 200, 300. Wireless sensor networks behave the same way as Wi-Fi or Bluetooth. But the key here is that distance stands for this communication. So what you need is to have enough nodes to communicate from one to other and then extend them into an infrastructure. For example, imagine here, you will have different lighting points and they are all really close, and even you will have the corridors to get some information, and you will cover a whole building, but this kind of multi-hop system, which is called multi-hop because then you have one hop, other hop, and 3 hops. And this way, these networks can be deployed by using theoretically 65,000 nodes per coordinator. That's far away from the reality. The reality it's between 4,000 or 5,000 devices per coordinator, just because of the low bandwidth we do have. But here, there are, for example, when talking about free air conditions, which are the best conditions you might have in a path outside any building and without anything to cut the signal, you would probably have between 400 or 500 meters. And when you get into a urban area, that would reduce until 100 and 150 meters. And when you go indoors, that depends a lot on the way the building has been constructed, has been built. So it depends on it has the same features, the same performance as the Wi-Fi and Bluetooth technology in terms of distances. They are pretty the same because they operate in the same frequency band, and that's something which is banned for law. The law sets the maximum transmit power, and you can't over transmit over it. The key here is that you have this kind of solutions and multi-hop networks. That's the reason. Another question? Did you sleep?
What kind of devices can you use as a medium? I don't remember the name of the blue one in the other picture.
This one?
Yeah, the one. For example, a mobile phone able to reuse it as a
Sensor.
not as a sensor, as a can you take the picture? Yeah, as a full function device.
Yes. Here, these nodes, router ones must be full function devices. They cannot be reduced function devices. The only one who can be reduced function devices are end devices.
It can be, for example, a mobile phone used as a full function device.
Yes.
And how many end devices can be connected to a mobile phone, for example?
Yeah, it is said that around 512 devices to each one. But what happens to smartphones is that Zigbee technology or wireless sensor technology is not currently included into smartphones. It is thought that in the following years will appear several smartphones which will have this kind of technology, and then you will probably be able to create wireless sensor network solutions around a smartphone. This is one of the fights of the Zigbee Alliance. They are trying to make this technology to be included into the hardware of our mobile phones.
So they are actually use it as end devices.
Yes, you can use it both as an end device or as a router. It depends on your necessities. I mean, probably as a router because your smartphone is not a low power device, so you will probably take the most of your device if use it as a router rather than an end device, because you are going to charge it every day or 2 days. So there's no, the problem here about power consumption is that, these devices, especially in devices, the ones who have a sensor, they are often placed in very specific places which are not easily reachable. You need to use a crane or stairs to get to a point. So once you stand there, you don't want to get back to it until it has passed several years or several months at least, because they are placed into different and difficult places to access.
Is it when you start measuring, when it's stopping?
No. What you can do, what you can tell them is how often do you want them to measure, and each time they give you a measure.
Is on off thing?
Yes. Yes. What happens is that
Fast or?
You can set the sampling time in each one. When talking about any devices, this one they won't probably have sampling time because they are always connected. So there is no need of setting sampling time with routers. When talking about end devices, what you can tell them is how often do you want to measure. If you set them, I want to measure every second or every 10 seconds. You will have the measure every 10 seconds, but at the same time they are giving you the measure, you can tell them, now you're going to give me your measure every 30 seconds. And then they will not communicate to you until 30 seconds have passed. So in this way you can configure your network dynamically. This is the way. For example, if you're talking about another important thing about end devices and the way we act to them is that if you, for example, you have a light controller as an end device which transmits every 10 seconds, once you give the order to switch on or switch off a light, you will probably have to wait 10 seconds till the light is switched off or switched on, depending on what you told, because they are not going to communicate to you until their sampling time has passed. So these are not suitable for real-time applications. I'm talking about real-time that you need a response in milliseconds or below second communication. But here with routers, yes, you can, because they are always connected. So once you give them an order, they will answer you immediately. I promise next part will not so hard. Will not be so hard. Next part is going to be about applications, and well, it will be more interactive. I will ask you for some ideas and your thoughts about this. Now I think it is a good time to have a break. Then
10 minutes.
10 minutes will be okay.
Oye, una cosa que a la mañana estoy con una niña y una cosa que nos impulsa tratando, que pone que se exige a los alumnos nuevos conocimientos de Python. Eso me ha dicho.
Me ha dicho Ignacio que habían programado Python ya en alguna aplicación móvil o no sé qué. No, pero que no era muy. Me dijeron que habían programado, pero que tampoco eran programadores. Entonces va muy a la práctica. O sea, esto va por aquí, esto va por aquí. Pero habéis programado algo, ¿no? Mi compañero otra vez muy guiado.
seguimos y bajamos de igual mira, ¿no? Si vais a bajar todos, seguir todos. No, no lo haces, Fernando.
Ah, está bien. Bueno,
No me acordaba de lo que era ser alumno. Sí, la S490. No, ya me dicho por aquí, porque digo que se dije a ver, como en los dibujos los cambios y la y dije, ¿qué tiene programadas ya?
Mañana una cosa.
No, no importa, no.
Sí, para